Welcome to Chapter 4.8, the last video for the chapter, Attractive Forces in Compounds. Okay, first I want to start by saying that what we're going over in Chapter 4.8 are not bonds. They're not new chemical bonds. Okay, we've looked at ionic bonds, covalent bonds, and within covalent bonds we have polar and nonpolar covalent bonds. Okay, but we're looking at the attraction between molecules. Okay, if we have two covalent compounds that are polar, they can have attractive forces called dipole-dipole attractions. Okay, and one of the strongest dipole attraction, or is the strongest dipole attraction between two molecules, are called hydrogen bonds. And this is when you have hydrogen atoms are bonded to very electronegative atoms of fluorine, oxygen, or nitrogen. Okay, so the key thing here and what you want to remember is that it is fluorine, oxygen, and nitrogen. Okay, so you have a hydrogen bonded to a fluorine, oxygen, or nitrogen. Otherwise, it cannot be called a hydrogen bond. Okay, I don't like the term bond, okay, because why I said this earlier, okay, that's what they're called, but these are not true bonds. These are not true covalent bonds. These are attractions between two molecules. Okay, hydrogen bonds are one of the strongest forces between molecules, and they play a major role in even the shape of our DNA. Okay, so we have this hydrogen bond. This is showing an attraction between two molecules. Okay, and so just to get this even more clear here. Okay, so if we look here, we've got a partial negative charge on the oxygen. Okay, and you may be wondering, where did that come from? I know I've noticed that from maybe last video. Okay, it's the fact that oxygen is more electronegative than hydrogen. Okay, so this is more electronegative. If you need to refer back to that video, please do so on electronegativity. It was the video for 4.7, I do believe, and 4.6, excuse me. Okay, and then this hydrogen is partial positive. Okay, so the oxygen is winning the tug of war. It's pulling the electrons closer to itself, giving it a partial negative charge. Okay, if we also remember, unlike charges or opposite charges attract. So this negative charge is going to be attracted to the positive charge on another water molecule. Okay, so that is what a hydrogen bond is. But the hydrogen has to be bonded to a fluorine, an oxygen, or a nitrogen. Okay, so if we look here, we've got hydrogen bonded to fluorine, and we have this is our hydrogen bond. Our fluorine is the most electronegative element, so it's pulling electrons very hard to itself, and so it's got a partial negative charge. And then the hydrogen has a partial positive charge, and so the attraction, we have these opposite charges attract, and so these are very strong attractions. They're also responsible for the high boiling point of water, because water, here we've got water molecules here, they hydrogen bond to themselves, and so actually when you're waiting for water to boil, you're waiting for those attractions, this hydrogen bonding attraction to break is what you're waiting for. Okay, dispersion forces are weak attractions between nonpolar molecules. Okay, so we've discussed what's nonpolar, we've gone over that, so there's not a large difference in electronegativity. And these are just temporary dipoles that develop when the molecules bump into each other. Okay, so they're all kind of moving, you know, the hotter, if you add heat, they're going to be moving faster, okay, but just your typical dipoles that will develop and when they bump into each other. These are very weak, whereas our hydrogen bonds were strong. But it makes it possible for nonpolar molecules to form liquids and solids. Okay, so let's look at we have our covalent bond, ionic bond, so we're not too concerned. These are much stronger. So bonds, this is just showing strength. Bonds are the strongest attraction, and they're between, you know, the atoms in the molecule. Okay, so we're not talking about bonds here. So we've already discussed bonds, but they're very strong attractions. Okay, But for our attractions between molecules, okay, so here we've got hydrogen bonding. So this is the strongest of our dipole-dipole. So these are our dipole attractions. Okay, hydrogen bonding is the strongest. Then comes dipole-dipole. Okay, and then dispersion forces. These are the temporary shift of electrons in nonpolar. So here's some examples. This would be nonpolar because we have two fluorines that are attached to each other. This would be like the attraction of fluorine to itself. So if we have hydrogen bonding, this is when hydrogen is bonded to fluorine, to oxygen, or to nitrogen. Okay, so we showed this previously, and this is the strongest of the attractions. Okay, and then we're going to talk real briefly, just so you guys know what the dipole-dipole attraction is. This is basically your polar covalent molecules. Okay, they're non-metals. Okay, so all of these here are non-metals. Okay, so all of these attractions here we're talking about are non-metals. Okay, but this would be like if you had two HCl molecules. So we would have HCl let me get this out of the way real quick. Okay, so we have this would be your dipole attraction. Okay, and all a dipole is, hopefully we'll clear this up if you have a question on that. But all the dipole is basically showing these charges. These are dipoles, meaning there's an unequal distribution of electrons. Okay, and so we know that chlorine is more electronegative, with a negative charge, a partial negative. So we have a partial positive and a partial negative here. Okay, and so this would be our dipole attraction. Okay, it's between the partial negative charge on chlorine, because it's more electronegative, and the partial positive charge on the hydrogen. Okay, it cannot be considered a hydrogen bond attraction because it's not bonded, the hydrogen is not bonded to fluorine, oxygen, or nitrogen. Okay, so it cannot be considered hydrogen bonding. Another example is this example here. So we've got bromine and chlorine, and if we look at their electronegativity difference, we see that they are nonpolar, but our chlorine has a partial negative charge, the bromine a partial positive, and so they attract where the dipole is here, and this is the attraction between the positive and the negative charge. So basically what sums all of this up is the fact that electronegativity induces a dipole and in your polar molecules, and you can either have a hydrogen bond attraction or a dipole-dipole attraction, depending on if you have fluorine, oxygen, or nitrogen, or if you just have two nonmetals that do not include those three elements. Melting points correspond to these attractive forces between molecules and compounds. So they're lower, melting points are lower for weaker forces, such as dispersion. So dispersion forces are the weakest. And they're higher, so melting points and boiling points, as a matter of fact, are higher due to strong attractive forces. So the higher the melting point, the higher the hydrogen bonding would be. And they're highest in ionic compounds due to strong attractive forces between ions. Okay, so hydrogen bonding is not as strong as your typical ionic bond. Okay, so this just shows melting points of your ionic solids. We talked about table salt, and we have magnesium fluoride here. So these are actual bonds, what we've discussed previously in the chapter. So these are actual ionic bonds, and they have very high melting points. Okay, if we have hydrogen bonding, then there's a significant jump. Okay, there's lower melting points. Okay, but they are still higher than compounds that would just have dipole-dipole attractions. Okay, so here's your dipole-dipole attraction. These are polar covalent compounds. Okay, but they can't hydrogen bond because they do not contain your oxygen, nitrogen, or fluorine. And then dispersion forces have the lowest melting points, okay, because they have the weakest attraction. Okay, and these would be things like Cl2, F2. These are nonpolar covalent compounds. Okay, so the stronger the attraction, so ionic bonds have the strongest attraction, they have the highest melting point, and as we go down, the attraction decreases as well as the melting point. Okay, so let's see if we can identify the main type of attractive force that are present in the liquids and identify them as ionic bonds, dipole-dipole, hydrogen bonds, or dispersion forces. Okay. So the first, we have two nonmetals. We know we have covalent compounds. Okay. We also know that we have a difference in electronegativity. So we're going to have a polar covalent compound. And this would lead us, okay, so ionic bonds, this is going to be a metal and a nonmetal. Okay, so it can't be this. Okay, and now we have a dipole. Options are dipole-dipole, hydrogen bond, or dispersion. Okay, it's not going to be hydrogen bonds because we don't have a hydrogen. Okay, and then dispersion would be if it was a nonpolar compound. Okay, but we know that nitrogen and chlorine have a difference in electronegativity, and so we're going to have a dipole attractive force. Okay, so next we've got H2O. It contains a hydrogen and oxygen, so all of these options here are only for nonmetals. So we have a nonmetal, we've got a covalent compound. We also know that it's polar covalent because we have a difference in electronegativity. But we also have a hydrogen, so we showed this example earlier, bonded to our hydrogen bonded to oxygen. Can't remember which one I said first. Okay, and so we can hydrogen bond. So we can have an attractive force of hydrogen bonding. For C, we have two nonmetals, which means that we have a nonpolar covalent. We have a zero difference in electronegativity, and so the attractive force that would be between two of these Br molecules, bromine molecules, would be dispersion. This is our weakest force. Okay, KCl, this is an ionic compound because we have a metal and a nonmetal, so it's the strongest attraction, and it is the ionic bond. For E, we have two nonmetals, so we have three options here. Okay. So first we want to think, could it hydrogen bond? And the answer is yes, okay, because we draw out the structure. You can test yourself on this. If you want to write out the NASB theory, be sure you know how to draw ammonia. Okay, but if it's a hydrogen bond, so there's my hydrogen bond, it can hydrogen bond because it is a hydrogen bonded to a nitrogen, and that's the definition and one of the options for hydrogen bonding. So if we draw in our nitrogen is more electronegative, so it's going to be pulling electrons harder, so it has a negative charge. And our hydrogen's always going to have the partial positive charge. So we have this positive and negative charge attraction, and this leads to hydrogen bonding. Okay, so to sum this up, if you have an ionic compound, it's an ionic bond, it's a metal and a nonmetal, and it's the strongest. If you have a hydrogen bond, this means that you have a hydrogen bonded to an oxygen, nitrogen, or a fluorine. Okay, so here We've got examples, and this would be an attractive force that would be in between these molecules would be hydrogen bonding. Okay, if you have a nonpolar covalent compound, there's zero difference in electronegativity. This is going to be dispersion, which is our weakest attraction, okay, for our nonmetals. Okay, all of these last three options are for covalent compounds, for nonmetals. Okay, and the last is the dipole-dipole, which may be kind of the hardest for you guys to see, but basically it's going to be a polar covalent compound, okay, but it's not going to contain a nitrogen and oxygen or fluorine combined to a hydrogen. Okay, so it can't hydrogen bond, but yet it is polar, and so it's considered to be dipole-dipole attraction. Thank you, and this concludes the videos for Chapter 4.